Okay, so Rainbow is like these kind of 6 updates. It's like double deep Q learning, dueling deep Q learning, nosy nets, and look ahead buffer, prioritize experience replay, and distributed Q learning. Now, these 6 improvements are applied on the traditional deep Q learning agent. So this is the traditional deep Q learning agent, and the double deep Q learning. What it does here, you see, we just take here the argmax, right? Oops. So this, in the original one, we just take the maximum A of the Q function, right? And for the double Q learning, you take advantage, like you have 2 Q functions, right? You have 2 models, right? So first you calculate the argmax of A just as this one before. You just exactly take this one and you plug it into the other, into the target model, and then you take the gamma. And this is like, because of the way it's coded, this is enough to go from Q learning to double Q learning. These few lines of code. So what we do, we estimate the value of our next state, right? We have the next state and we put it in our normal model. So we say it's the maximum. So we get the maximum what our model thinks it would be the X. This would be on policy, exactly. So we take the actions of our Q learning model for each state. So it would be an on policy step. And we kind of detach it because we want to do some funny stuff with it. There's like a PyTorch thing. And then we say, okay, we take the target again, we take the target model for the calculating the YEs, right? Because we wanted the stationarity. And then we calculate, okay, this is the target output one. And then for the target output one, again, we take, here we select the actions we want, right? So this is what we select for the next state, right? This is just in the Q learning, we put the states in, right? And then for each state, we take the maximum A. But instead of taking the maximum A, we take the action our model would have chosen. So we are on policy. So here, instead of doing the maximum, we just use the gather function, which basically says, okay, for each row, give me the action our model would have chosen. And then this is going to be our maximum next Q. And then the maximum next Q is then calculated for doing the loss and so on, so on, so on.
How does that help us? How does that help us?
It just gives you a better estimate of your future Q value.
But we already got the maximum, right? Then how does the next step? The next step is just going to be a random step that we could have taken. Whereas we've already got the maximum, so how does a random help us to understand better?
So you see, this is the target output, right? From the target model. So in the Q learning, we would take the maximum of each of these rows, right?
Yeah, we do that.
And then instead of taking the maximum, we take the one our agent would have taken. And that's the difference. And it helps the model to learn faster.
Florian, do you mind making the...
Oh, sorry. Oops.
Oh, that's the one. Yeah, this looks fine. Thank you.
And as you see here, for the trained model, it just learns much faster. And then there's like...
Just for the last one, we observed that the value sort of decreased. Is that...
Yeah, they overfit.
Okay.
Like, I think I had no time to do hyperparameter tuning for each one. And I think you can add some dropout layers to the neural network, or just make the neural network, like the input are four features is the input, right? Before, when I was getting the optimal policy, I think I used a layer with just 8 or 16 hidden layers. It works better, because if you make a too big network, you just overfit. And that's what you see here all the time happening. Like, it's doing really, really well, and then it does crap. So let's say this is kind of the feature generation part, right? So we always select it into two, we separate it into 2 parts. So in the Duelling Deep-Q learning, you kind of do the advantage function. And then And the way it is achieved, I take the input, the processed input features, and then I split it up into two streams. And one stream kind of calculates the advantage function of each action, and one stream calculates the value function of the state.
Advantage function would be?
I'm going to talk a bit about what the advantage function is. And then you just aggregate it to get your Q values for every state. So what is the advantage function? So basically the advantage function is like, it kind of pays attention to a little bit. So you say you're in a certain state and you perform an action, right? You can just be in a very, very, very favorable state. So all of your actions have a very high return value. But what you want to do is select the action or use the action that just performs better than the average, right? So if you have kind of like extreme positive or extreme negative values, then just saying, okay, I take the one that has the better over the average, you kind of, then you want to take this. So what it does is say, the value here, for example, the value, it pays attention to the road, right? And then say, okay, depending on the road, I have to turn left and right. And here, the advantage function pays attention to the cars in front. So if it's like a car directly in front of you, it just tells you, okay, you avoid the cars. And you can think of it a little bit of normalization, right? So I take the value state and I add the advantage minus the mean of all advantages. So it just, you kind of take the advantage function and you average it. And here is just this FC layer pretty much stays the same. And here now we have two streams. Like one is the value stream and one is the advantage stream. And we have the output is again just the same. And the forward.
Sorry, just initially when you said that you would take all the pre-processed data and split it into two, so both of them would be looking at different states then, right?
They look at the same state.
But you said, but if we split the states, the one that we got from pre-processed, so both of them will be fed the same state?
Like, it's like a fork, right? So you do your forward layer, your forward layer, your forward layer, and you get a hidden input. And then you have one layer that takes this hidden input as an input, and it calculates the value function. And then you have one layer that takes this exact same hidden input and calculates the advantage function. So you kind of, you fork it off. And this is exactly what we do. We take the value stream, we get the value function, and we take the forward stream, we take the advantage function. Yeah, exactly. So the output gets the hidden state. This is the hidden state, right? And then we calculate the value, we calculate the advantage, and we return basically value plus advantage minus advantage mean. So the advantage stream is basically for each action, and the value stream is like just one value, it's like the state value. And this does really bad at the beginning, and then once the epsilon goes down, it just does really well afterwards. And also it stays really well for a long time. Whereas the other one, see, this one is the one that got almost the optimal policy, like 489, because you lose 10 points when you're done, when you're finished. So it's gonna be like this. This is like close to the optimal. And then it overfits and then crashes, and then it's kind of, there's like, you see there's some kind of instability here.
Like, since we know what the maximum, at least the maximum is there, so can't we sort of stop it when it gets to that level?
Yeah, it stops by itself. Like the game is over when you reach the maximum store. And then I'm gonna talk about noisy nets, and then gonna talk a little bit about what we're gonna do next session, and then you can ask questions or we go on. So here is like a table of contents. If you're interested, like you can switch to anything we have, and yeah, these two. If you have any questions, you can just ask me online. So you can look through the code and try to understand what's happening. So noisy nets is just it's very unrelated. I feel like for the deep kernel parts, like there are Gaussian or noisy linear neural network layer. So basically, in a traditional neural network layer, you have your input, and you multiply your weight matrix with the input, and you add some bias, right? And then you get your hidden state. And in the noisy one, you have like your input, and you add some kind of noise to your weights, and you add some kind of noise to your biases. And then when you finish training, you just remove the noise. And that's it.
What's the advantage of doing this?
You kind of reduce overfitting.
It's kind of like a generalization of dropout.
Yeah.
Instead of removing the weight, you deviate from the.
And I think, I don't know if this, so the noisy net implementation, I just got it from someone online. It's like on PyTorch, it's not part in the standard library, but it's a merge, it's a pull request. Like it's a request on the PyTorch library that they put this kind of noisy layer as a standard layer in PyTorch, but it isn't there yet. And I just put someone's implementation of it, and I think, but I'm not sure, that also you can do some kind of simulated annealing. Like as you go, you reduce the noise. So you will see for the agent, with the noisy agent, your epsilon is 0. You don't do any epsilon because you have the noise from this here. You have this noise. So you don't really need to do kind of epsilon. You don't need to select a random action because this one already makes you select random actions.
But this is work better than having an epsilon? Or competitive?
I don't know. This didn't work better. I don't know what the reason was.
Okay.
It just didn't work better. So far, the best one from all the ones I implemented was the Dueling Deep-Q learning. So the Dueling Deep-Q learning extends. The agent I do is a double Deep-Q learning agent, right? We can put here the normal Deep-Q agent, then it's like Dueling Deep-Q. But if you put the double Deep-Q agent here, because the double part only says, okay, how do I calculate the max Q, right? So this is basically double Dueling Deep-Q agent. And this is what I mean, like it becomes like you create the interface as fixed, it actually becomes like a mix and match puzzle piece kind of thing. Like Lego, think of it like Lego, right? And you just put in what you want. And this is basically just the noisy net. I got it from here. This is actually some kind of noisy net implementation.
Isn't that like the Ornstein-Uhlenbeck process or something like that?
Excuse me?
Isn't that some almost? I mean, I remember doing this, but I thought we used some sort of Ornstein-Uhlenbeck process for these like random things.
Yes, yes. But I think he does use like normal distribution. So he has some mu and some sigma, and just add some normal noise.
Okay.
It is. I've seen it online. This is how I think people do it for the optimization. But here it's like a very simple implementation. You just add the noise to you just make a linear, and if you do training, you just have your weights and you add sigma times epsilon, right? And then you have your bias. He just has like some random noise he adds on top. And for the noisy dueling, basically it's just for the output layer. I just change this kind of noisy linear for the advantage stream and the value stream. And here you get like, see, this basically went from not learning anything, having like really shitty reward, and as you see, the epsilon here is like 0. So you don't need the epsilon. It's just random. And once it picks up signal, once it learns, it just, you see, it's just switch like from -1 immediately like to 300, 400. Like this is the 489 is the maximum reward you can get. And you see this one, it doesn't like overfit because it has the noise on the weights, so it does less overfitting. I'm just gonna talk a little bit about high level here, just very quick, like cliff notes. So basically, we look always one step ahead, right? And for multi-step learning, you just look n steps ahead. So you take the reward n steps ahead, and you just have the sigma n. It's kind of like what you do. The way I do it, I use DQ. So this is like two cool things I want to show you. DQ is like a fast queue. It's a very fast array, and you can shift and move through the array super fast. You can do 10,000. It's like a ribbon, right? It's exactly what I described before. So you shift it, you move it by one. So say if the queue is an array, you say it's 1, 2, 3, 4. And then you say, okay, this array position 0 is 1, position 2 is 3, and so on. And then you can say array shift, and then depending which direction you shift, it says 2, 3, 4, 1. And I use this basically to say, okay, if I want to do n step ahead, I shift the array each step by one step, and I multiply it with the future reward discount. And then this way I get the updated reward. And then when you do the calculating this value here, you use basically this shifted reward where you look n steps ahead. And that's it. And for named tuples for Python 3.7, because now these named tuples are unmutable, so you cannot update the reward inside. So what I do each time for the buffer is each time I put something in the buffer and I say I'm looking n steps ahead or if I have more than 3 items in the buffer, I update the reward for the old data point, right? I shift the whole array by 3, I update it and shift it back each time I updated the position before.
So maybe like to clarify, the previous one we take one action, and then for the next state we estimate the Q value function, the estimated reward with the value function. In this case, you take 2 steps and basically you receive 2 rewards, right?
No. You still take 1 step. After 1 step, you sample 32 data points, but you just don't sample the recent data points because you don't have the future steps. And once you are having more than 3 steps, you say you look 3 steps ahead, you take only the ones where you have updated the reward. And each time you take 1 step, you push the queue, push an item in, and all the one data point that's like 3 steps behind, you just update it with the reward. And then you add this data point to the ones where you can draw.
So we have like basically step ahead prediction thing, right? Which if you generalize that goes to like, let's say Monte Carlo. If you go like infinity, then like basically you don't update your queue.
If you select it to infinity, your model will never learn. Because you never have infinity look ahead.
It will not terminate, right?
So you see, the only thing I hear change is the buffer, right? So the QLearning, the underlying QLearning, it stays identical. How the arrow function, everything stays identical. It's just what is the reward for my current step.
Whiteboard marker. So
Say my first step is empty, right? And my next step, I have my first data point, and I do nothing. And then my next step, I have my first and my second one, right? And the next step, I have my first, my second, and my third one. And then I say, okay, I have my next step, I have my first, my second, my third, my fourth. And what I do, this is just how I implemented it. People implement it differently, but I think the way other people implement it is very inefficient. Because what they do is, each time they just normally fill it up. They don't do any update. They treat it as unmutual, and then they draw, and then each time they draw, they kind of update all the weights, and then just draw from the ones they can draw.
So people online didn't see that. Could you say that once more on the board, please? For people online.
Sure.
Yes.
So you have an empty one. This is where you start. And then you do 1 step. You put your transaction into it. And you can say you have a batch size of 32. You kind of have nothing you can draw from, right? And then you say, okay, do my next step. And then I have 2 in my thing. I put another step. Oh, I have 3. Still nothing draw. And then I put mine in. And then I have here. And now I have the first time where I can say I can look 3 steps ahead. What I do is I update this one. So now this is an updated one. Now this is a real data point I can sample from my sample. And I keep doing this until I have like A1 to A prime, like the batch size, right? And then I still have like my A whatever batch size plus 1.
Yeah,
A
true,
batch
true.
size
So
plus 2. and so on. And then I say, okay, you want to draw a sample? You just sample from
Yeah,
these.
but that's the logistic to how to implement it, right?
Yes.
But what I'm talking about, the idea behind that.
Yeah.
So the idea is that in the previous one, you take one action and you receive one immediate reward.
Yes.
In this case, you receive 3 immediate rewards.
No, still one.
Each step receive one, but like you use 3 of them to update your Q function. That's what I'm saying,
exactly,
right?
yeah,
And you estimate the 4th basically reward with the Q function. So basically, in the previous one, you take one action and then you estimate the next state with the Q function. In this case, you take 3 steps and the next state is estimated with the Q function. So
kind of like your reward.
A chess player would play chess, you know, like they think 10 moves ahead or even 5 moves ahead or 3 moves ahead, and they make the best.
Yeah, so but like, and still I think
kind of, but there's also like model-based reinforcement learning. So say AlphaGo, where they kind of simulate the game.
Yeah.
And then they're gonna search the space of all possible 5 future
but like
steps.
if you increase this number of steps, right, to the time that it finishes, then you get basically Monte Carlo.
Yeah,
converges to Monte Carlo, basically, because
more or less.
Yeah.
Well, the updating is still different, but yes, in Monte Carlo you draw it down to the end of an episode.
So what's the motivation for
it's hard to say. It's hard to say because the replay buffer stores multiple episodes at the same time when you draw from them, right? So if you send it to the maximum, right, then you play a whole game and then you store and you update all the weights in that game, right? And so on and so on and so on and so on, right?
So there's like the TD0 and TD1, TD lambda, right?
Yeah.
Isn't it the same thing, kinda? So in this case, like it's a case step ahead, and then you can basically average over all of them, and then you get like TD lambda thing, right?
Kind of, yeah.
Yeah.
Yeah. It's like it's a TD lambda thing.
Yeah.
What's the motivation behind this approach?
Like you want to look a few steps ahead. You don't want to take like, so the value function is kind of not really, if you look at one step, the biggest contributor to your value function is the immediately direct reward. But the value function you want to capture kind of the preference of the state. And by looking a few steps ahead, you kind of decouple it a bit from the immediate reward, right?
So yeah, by this, the agent tends to be like more futuristic. So it looks more about future, not just immediate.
So even in those 3 steps, you will take maximum for each of those steps.
Sorry?
Like when you looked at one action, we looked at the maximum of that state and action. So now if you look at 3 steps ahead, so what are the actions that you want to select?
So basically you follow the same rule, you take the actions, but after taking 3 actions, you calculate your Q function and then update the 3 steps before, Q function. Okay. So you wait three steps and then update.
So is this maybe used to reduce bias then? Because when you have more steps ahead, then you rely less on the estimates.
No, that's what he was using, basically the batch idea, right? He was not updating it based on one. He was taking a batch and then updating.
But I think what he means is like, the bias towards rewards. So like you're less biased to the immediate reward.
Yeah.
You're just more biased to like the general future. Like you put a bigger weight on your expected future reward and a smaller weight on your direct immediate reward.
So fundamentally, it's in the middle of the Q policy and the bandit program.
Kind of, yeah. So yeah, this kind of concludes our QLearning part. So next session, I think I'm gonna talk about gradient policies, and I think instead of doing the actor-critic model, I think we're just gonna do like reinforce, which is kind of the core gradient policy method, and then we do the deep deterministic policy gradients, which is a really great method, and it really helps you out. And if you understand this algorithm, taking it to the next step for the actor-critic, it's gonna be more like almost similar, like taking it from QLearning to Dueling QLearning. So this is kind of very, very similar to an actor-critic model, similar issues. So, and then I think I'm gonna talk a bit about like how to build your own AI environment, like AI gym environment, like, because in the end you want to take all this what you learned, you want to take it and you want to take it to your own problem, and this part is going to be like the coding, and then we're going to look a little bit how did people play around with the reward functions for different problems. So it's going to help us understand a little bit how to make your own custom reward function.
Sorry, I thought this was the.
So when you say custom environment, you're saying for the real world problems.
Yeah, kind of real world. We're going to look a little bit at real world problems.
So like the
Cool, thanks. Thanks everybody.
Thank you.
but like